Good morning, ladies.
And the objective of this lab today is to measure the MTF for diffraction limited systems. The basic definition of MTF is this equation, which states that the modulation of the incoming wave is divided by the modulation of the output wave. MTF is all based off of the diffraction phenomenon, which can be summarized using Huygens wavelengths, which states that you can construct a spherical wave, like right here, using a summation of individual smaller waves, or spherical waves. The constructive and destructive interference of these waves distorts the wavefront and causes Fresnel zones patterns, as shown here. This is n sub f equals 1, where we have a dark spot in the middle. This is n sub f equals 2, where we have a light spot in the middle and a dark ring around it. These Fresnel zones are characterized by this equation, which states that the number Fresnel zone number is equal to the radius of the aperture squared divided by wavelengths times the length away from the aperture. And we see that as you go closer to the aperture, the number of Fresnel zones increases very rapidly. Here's a graph showing the MTF, and on the x-axis you have spatial frequencies, which is cycles per millimeter, and the point which crosses the x-axis is where the cutoff frequency is. And on the y-axis we have the modulation.
For the experimental portion of this lab, we used a knife edge test as we had done in previous labs, where we basically just move the knife across the beam waist and collect the irradiance and measure that over knife position. Here is a typical graph of what you get from the raw data for the knife edge test, and here is the LSF plot, which is essentially the slope of the knife edge trace. Here's the governing equation showing that, and as you can see, it's more or less a Gaussian-esque kind of shaped plot. Concerning Fresnel zones, they are specified essentially by half a wavelength OPD boundaries and an aperture. Governing equation is OPD equals the half a wavelength times integer m. And you have here an example of a diffraction pattern. And you have the radius a right here. And you have a Fresnel number, which is equal to a squared divided by lambda divided by L. And L is a distance from the aperture to the pattern that is being observed. Now, one thing that helped us find out how many zones that we were looking at when we were doing the experiment was if we saw a bright spot, it was an odd amount of zones, where if it was a dark spot, there was an even amount of zones. And an important correlation is L is related to a squared, as we will talk about later. In order to find best focus, we used the dark spot method of sorts. We first found the -1 wave dark spot pattern and the +1 wave, which are 2 and -2, and Fresnel numbers. And we located those locations, put them in focus, and found the average between that. And the approximate middle between those 2 points is where the best focus is located.
For this experiment, we used a spatial filter and a collimation lens. We used an NA of 0.4 to capture the beam, and we used a collimation lens of 300 millimeters. We folded the beam this way 9 degrees with a mirror, and we placed our test lens over here in our aperture, and we found the plus and minus 1 defocus positions by observing doing the black dot test. You can't really see the fringes right now, but you did before focus, which would have been here, and after focus. And then once you found those, you placed the slit on the rail at those focus positions, and you took power readings of the beam. Here's the Fresnel diffraction pattern at best focus with our test lens. Notice the bright spot in the center, and here's one wave of defocus. There's a dark spot in the center, and minus one wave of defocus. Another dark spot in the center. This is before best focus. Here's our beam expander numbers. We chose them such that our beam diameter was sufficient to fill the clear aperture of the test lens. We chose our area disk diameter to be 230 microns so that we could sufficiently scan through it with 10 micron increments with our knife edge. These are our results at best focus. Notice the MTF closely matches the theoretical MTF from code 5. This is at -1 wave of defocus. And the graphs closely match once again. And here's at +1 wave of defocus.